Okay. Okay, so this is Unit 7 text corrections. So first, what the heck? Yeah, first question was, first question was, okay, here student wants to determine the spring constant of the spring constant K of the spring. Indicate which quantities could be graphed to determine the K by using a best fit line. You may use the remaining columns. Okay. So here I put t squared and m because we know that the the we know that the period is proportional to is wait we know the period is directly proportional to mass and inversely proportional to k. So if we manipulate the equation, we have the k is equal to some numbers and then t squared, the period squared over the mass. So that's how I got this. This is right. So this 1.1. Next question. On the grid, plot the appropriate quantities to determine the spring constant by using a best fit line. So like I just said, t squared over m, and that's what I did here. See t squared and then m, and then here's the line too at the points right here, and looks pretty close to that. So that's 3 points. And then yeah, see label the units. I did label my units for linear scale. Oh, I did do that. I used the whole grid, and then and then the straight line. So that's 3 points. 3 added 3, and here A3. Question is, use the graph above to estimate a value for the spring constant. So here I did do the math, and then here I got 20.778 newtons per meter, and that is k equals 20. So okay, I got that point plus minus 2. I'm in that range. Using the slope of the graph. See, I have here 1 over the slope, and then right here. Here I used the slope of the graph right here. That's where I got this. And then I plugged it in over here, 1.9. That's the slope, and that's how I got the answer. So I got those 2 points as well. And then part B. The question is, another group of students perform a similar experiment in which the same block spring system from trial 1 oscillates but in the horizontal direction. Frictional forces are negligible, and the students pull the system 0.8 meters from the system's equilibrium before the release, so it oscillates. Will this change in the experiment affect the value of the period of oscillation? So I put here, no, the period of the spring is only affected by its mass, by the mass that's hanging on it, and the spring constant. Pulling the spring more will still result in the same period because the mass and the spring constant are the same for both systems. And then this says 1.5 not different. Yep, I did that. 1.0% only depends on the mass of the object. Yeah, but I also said that. So it's 2 out of 2. Okay, next part. Last part. Describe an experimental procedure to determine whether or not the period of oscillation T for the block spring system is different compared to the one in block A. Include any steps necessary to reduce that. Give enough details so that the person can replicate the experiment as needed. Include a diagram. Include a diagram and the experimental setup. Assume equipment usually found. Yeah. So here, okay, I didn't include a diagram. It's just okay. Set up the horizontal spring. So I I got this. Let's see. What point is there for saying that? Okay, I did get that point, the very last point where to reduce uncertainty right here by doing it multiple times to reduce uncertainty. But for these 3 points, although I did mention it, as you can see here, compare the values of the periods, I wasn't really specific. Like, you don't even know which periods I'm talking about. So I didn't really get one of those points. And as well, using right here, using a meter stick and then using a stopwatch for these 2 points to specify that. But I just said to just do it instead of like actually saying to like specifically using the equipment. So I didn't get those points, so I got 1 out of 4. So total that's 1, 2, 3, 4, 5, 6, 7 out of 8, 9, 10. 10 points. 7 out of 10. Okay, thank you.